Alright, let's talk about vanishing gradients. To do so, we start out again with the chain rule in two notations. One is Newton's notation, which you probably know from elementary school, which says that the derivative of composite function f of g of x is given by the outer derivative times the inner derivative. In Leibniz notation, this looks as follows: df by dx is given by df by dy multiplied by dy by dx. The Leibniz notation has one advantage in terms of memorization. It's easy to memorize that if you think of this product here as being cancelable, so that you could cancel the enumerator here and the denominator here, even though of course in correct mathematics this is not allowed, but this is a way to memorize the formula. In high dimensions, multiplication here, so this is one dimensional, becomes a scalar product or a matrix vector multiplication or a matrix multiplication. So we already know the first case when x is a vector, so when f has multiple variables, then df by dx is given as the gradient, and this is given as this vector here. It's just a function, and its partial derivative with respect to all of the variables. When y is also a vector of functions, so when we have multiple individual functions that all have the same amount of variables and the same variables, then dy by dx is given as a matrix, which is also known as the Jacobian, and this Jacobian looks as follows: dy by dx, this is a vector of m individual functions and their gradients. So these are gradients, these are vectors, and then a vector of vector, depending on how you write it, this becomes a matrix. Good. Let's go back from the original, or from this general outline of derivatives to the recurrent neural network formulation. We know how this formulation looks like. We have the hidden state at time step t is given by the input vector multiplied by u, plus to this we add the previous hidden state multiplied by w, and then on top of that linear form here we apply our nonlinearity, and then the output y is given as the hidden state times v and a nonlinearity on top of that. And we omit biases for simplicity. Then if we want to go for the loss, we get a little loss at each time step, et, which is, if we have cross entropy loss, which we will generally assume, it's the minus logarithm of ytj. What is this j? We're usually in multi-level classification, and then j depends on t, of course, so at each time step we have a different class. J is the true class at time index t. So we have multi-level classification where the truth vector are one-hot vectors, and the index j says this is class number j, and then we get our loss depending on which probability we give out here. If we give probability 1 to j, to the correct class, then we have no loss, and in all other cases we occur a loss, with a maximum loss of if we give probability 0 to the correct class. And then the complete loss is given as the sum over these individual losses. So now let's go into derivatives. So why are we investigating derivatives? Because the derivatives of the loss function e with respect to our weight parameters. So this is actually what we are estimating by gradient descent, right? Not by gradient descent, by backpropagation. So backpropagation is giving us this, and it's giving us like a recursive formula. Now we want not this recursive formula because we want to do analysis, so we are not doing a recursive formula, but we want to get a direct formula, right? So we derive it in a different way. And why are we interested in this? Because for one thing, we want to see when is this thing exploding and when is this thing vanishing. When it's exploding, maybe you have a numerical overflow and then gradient descent will not work anymore. Or you have like 0 here. And then if you have 0 here, then this means, well, you're not updating at all, you're learning nothing basically. So this is the motivation why we could look at that. So now what is dE by dy? Because E is just a sum and the derivative of the sum is the sum of the derivatives. We have this formula here. So we have this formula as given here. Now let's look at each term in this summation here. Each term in this summation, we apply the chain rule on a formal level. So we're not looking on a content level. If we would want to look on that in more detail, we would have to spend more time on that and calculate everything out. So this would cost us a lot of time. So let's look at this from a formal perspective. From a formal perspective, we can verify this identity here. So this is the identity that we want to verify, and we can formally verify this quite easily by looking back to the chain rule, because we can cancel out the factors here. So this and this cancels out, this and this cancels out, and hey, the identity apparently holds. And also, if we want to do a little bit more look on the content level, we can also see that et depends on y. So this is the y here. Yt depends on yt. Yt in turn depends on hd. Hd in turn depends on w, right? So okay, so this apparently seems to be fine. Now we want to look at this term here, dht by dw. So what is dht by dw? So what we notice here, we have the w here once, but also ht minus 1 depends on w. So overall, what we get is we get this more complicated looking formula, which we're not going to verify now. So we would need a little bit more work to verify this, but it would not be too difficult overall, but it's also not necessary to verify that at the moment. So what you can see here is now we rewrote dht by dy, again using the chain rule, into a different factor, and this different factor here again like cancels out. You could like cancel that out, but then we have to sum over all time steps up to t. So we have to go from the first time step up to this time step t. We have to sum over these time steps. Not going to show the formula here, but okay, we have to live with that now that the formula should be true. So okay, and our main interest now, from now on actually, so now we have derived this formula, but maybe it would not even have been necessary to derive this formula. Our main interest from now on is just in this part, right? dht by dhk. What does that mean? So if we go, so first of all, this is a vector, because the top is a vector and that's also a vector. So overall this is a matrix, right? But what intuitively, what does this matrix mean here? It means, like all derivatives, it means what happens when I change hk, what effect does it have on the thing in the numerator, right? This is the denominator, this is the numerator. And what effect does changing this thing down here have on this thing up here, right? So this is the definition of the derivative in general. So and what we will find maybe is that okay, we'll see what we'll find. Okay, now we wanna look at this. So remember that ht is given by this formula. Cool. So let's do some more chain rule. So we have ht by hk, where k is k ranges from 1 to t, right? So k is smaller or equal than t, or maybe it is, yeah, it's smaller or equal than t. So what we do is we write this formula as a product of factors that differ exactly by 1, right? So you see here t minus 1, the difference is 1, so in each case the difference is 1, and this formula down here is easy to verify because everything cancels out, and then you're stuck with the original equation. And I think actually that yeah, good, good. Let's continue. So we have dHt by dHk is given as this product of individual matrices, which each have a time difference of 1. But the time difference of 1 is easy to calculate, right? dHt by dHt minus 1, that is really easy to calculate. Let's assume this would not be a vector equation, but it would be a one-dimensional equation. Then we could just go, as we did in school, inner derivative times outer derivative, and we get the formula. So what is the outer derivative? Well, it's sigma prime and everything that comes in here. So this is this part. What is the inner derivative? It is, well, if we derive that by ht minus 1, then this term here cancels, and this here is just w, right? So now we are not in one dimension, but we are in multiple dimensions, and the formula looks very similar. So if we want to verify this completely, we could look at a reference here, but we're continuing in this intuitionist mathematics that we have already developed. Good. So so this is basically like in one dimension, but we have this diag argument here, or this diag operator applied to this argument here. What is the diag doing? The diag, if you have a vector and you put the diag operator in front of the vector, it gives a matrix that is 0 everywhere except the diagonal where it puts the vector, right? So this is this formula, and we accept this formula for now. Good. So now we have an exact equation for DHS by DHS minus 1. And I write S here, by the way, instead of T, because you know the T was our upper limit, right? And K was our lower limit, and S is something in between. It's one of those factors, right? So we have our exact formula. So that's the formula here. So we could put norms on that exact formula, so we get that here. So now we can get an upper bound for this formula, so we can get an upper bound of the norm here by taking the norms of those two products. You know, this holds in general. If you have a norm and you have two matrices in the norm, then the norm is less or equal than the norm of each of the two factors, right? Okay, so this holds general. So we get an upper bound for this thing. Now, what we assume is, let's assume we have an upper bound for the norm of W. So we want to upper bound this thing here. So our matrix, depending on how we set it initially or how we constrain it, it could have small values, right? And so the norm could be smaller than 1, or it could be equal than 1, or something like this. And let's assume we also have an upper bound for the norm of the diagonal, right? So this for this term here, this upper bound is even easier to get, because in most cases, well, it really depends on sigma h prime, right? The derivative of the activation function, and we've already seen a couple of derivatives of activation functions. And in general, like for the linear activation function, the derivative was exactly 1. So if we have a linear activation function, this thing here will always be 1, so we have our upper bound like either 1 or 1 plus epsilon, right? Whatever you consider to be an upper bound. And we also saw that most of these derivatives, they were even smaller than 1, right? So and this thing here is just a diagonal with diagonal matrix with 0 everything, and the norm and the sigma primes given on the diagonal. So the norm is just like is a clear function of the diagonal elements. So if these are all smaller than 1, then the norm will also be smaller than 1. Good. So let's say beta h is our upper bound for that part here, and beta w is our upper bound for this part here. And now finally, let's assume we also have a lower bound for this whole thing here. Maybe this lower bound is given by alpha. So the whole thing here is greater or equal than alpha. So let's look at this again. Like let's write it down in a formula. So we assume that alpha is the lower bound for the norm of this vector that we are investigating. And let's assume, as we've already seen in this equation before, we already know that this thing here is less than or equal than these two vectors, and we just said, okay, let's bound these vectors in terms of beta h and beta w. Okay, so now we bounded one of those vectors, but we're still after this whole thing here, right? So now we bounded each of these vectors here. So these are t minus k vectors, right? So we have t minus k. So if this is 2, and okay, so this is, we have t minus k vectors here, right? So we bounded each of these t minus k vectors. Now if we bound all of them, so we have like each of these t minus k vectors is bigger than alpha, then the whole thing here is bigger than alpha to the t minus k, right? Because we have alpha times alpha, and each of those is smaller than this thing. So this thing that we're after for here, dht by dhk, that is bigger than alpha to the t minus k. And this thing, also each of these terms here was bounded by some general bound that holds for all of the vectors. So the whole thing is less or equal than beta h times beta w to the t minus k, right? And now we are already there. So we have our first result achieved not by rigorous mathematics, but by kind of intuitionist mathematics, and which says that we can get vanishing gradients. And how do we get vanishing gradients? Well, if this product here is smaller than 1, right? Beta h times beta w is smaller than 1. Then if we exponentiate that to a large number, and we set it like t is greater than k, let's say t is 100, k is 10, so we exponentiate that with a factor of 90, then a number which is smaller than 1 to the factor of 90 is basically 0, right? Like at least on a computer that is 0. And this whole thing is of course positive, so it would actually be 0 on the computer. And if we have this 0 term here, so we can go back to our original equation that we derived before, where if one such thing is 0 here, then it just means one term drops, which is not so much important. So our gradients do not necessarily have to be 0, because only one element of the one summand just drops. But what still happens is that dht by dhk is 0. And what does that mean? So this is a matrix, but it's 0. So all the entries are basically 0, because the norm is 0. Then also all of the entries are more or less 0, right? So what it means is that hk has no influence on ht. Hk has no influence on ht, and hk is the hidden state at time step k, and ht is the hidden state at time step t. And in hk goes xk, so the element that's coming in at xk, and in hk also go everything that's before hk, right? Like hk minus 1, hk minus 2, etc. So basically, if that thing is 0, then it means everything that has happened up to time k and before is not stored in ht. So our recurrent neural network forgets everything that has happened at time step k or earlier. And when does that happen? Well, that happens when under these two conditions that we outlined, like the the derivative of the activation function is small. It's smaller than 1. And maybe also our W matrix is a small matrix. It has small entries, right? If these two things happen, or let's say this thing here we cannot control, not control so very much, but if these derivatives of the activation functions are very small, then we're likely going to have a vanishing gradient. Okay? So conversely, we can also get a exploding gradient when this alpha here is smaller than 1, is bigger than 1, then we have here that becomes very large, so norm becomes here very large, so that's a very large matrix. We multiply that with something else, it's likely going to be very large. Then we add some additional stuff, it's likely going to be very large. So in this case really, it may happen that we get numerical overflow. But this is not so much of the typical problem that we encounter. More is like that we forget. And intuitively, I mean, now we derive this forgetting in terms of derivative, but intuitively, what you can imagine is you have a hidden state at time k, and now this hidden state has to go. You can, like, the RNN is a graphical model, right? So let's go back to the RNN, to an RNN illustration. So basically that's a graphical model. So let's say H1 is our HK, right? So the information flow has to follow this path. Then when we arrive at HT here, all of the information, or a lot of this information, gets lost. How does it get lost? Well, it gets lost because, as we said, because of the activation functions, right? So what's coming in here, like that's gonna get dampened. It's gonna get dampened again by the activation function, and it's also gonna get dampened maybe if our W is small in magnitude, right? So we multiply this here. So the information that was in there subsequently or increasingly gets lost over time. Good. So this is this. And where do we have time steps? Where do we have long distances in natural language processing? Well, just in many things, like just consider language modeling. We want to predict the next word. Let's assume a sentence like this one here. Jane walked into the room. John walked in too. It was late in the day. Jane said hi to whom, right? So we as humans, maybe we assume that this could be John. And here we have a long-range dependency. So if we want to predict the correct word, we really have to go some time step into the future. But if our network forgets everything at time step k, so everything that came in here is forgotten, and things that came in earlier is forgotten, then we cannot remember that we should say hi to John, right? And here this is a character level illustration. So here that's on the word level. So we have like between this word and this word, how many words are in between? 1, 2, 3, maybe 4 with the punctuation, 5, 6, 7, 8. So maybe around 10 to 12 words. But if we're on the character level, we have even longer range dependencies because like each word has 7 characters, let's say on average in English, and we have 10 words, then we have 70 characters, right? So in character level language modeling, even though that is quite appealing, the long range dependency problem becomes even harder and even more challenging. Good. So we already said that the derivative of this activation function is important, and this derivative of the activation function, this gives our upper bound beta h. And here again we have 3 activation functions: linear, also called identity, what we also call identity, then the sigmoid, which is also called logistic, and the 10h. We look at the derivatives, and we said there are 3. And we look at the derivatives, and you see like the identity has good derivatives, they're always 1. The logistic has very bad, like the sigmoid has very bad, they're very, very small derivatives, and the 10h is better, especially around 0. So in total we have 3 regions of different quality. Region 1 is when the derivative is very small, then we have vanishing gradients, right? That's what we already talked about. If this sigma h is very small, we get a small upper bound, which is smaller than 1, and the gradients vanish. If sigma prime is bigger than 1, we have exploding gradients because we have this to the power, like we have 1.2 to the power of something, that explodes. If it's exactly 1, then we're in the good region. 1 to the power of 90 is still 1, right? So everything's flowing smoothly. So actually we should choose the linear activation function here, well, where the only problem is if it's linear, then of course the problem is that we're in a linear model, and linear models are suboptimal. So maybe the ReLU function would be a better choice, which is partly linear and partly it's not linear, right? So now keep in mind that the vanishing gradient problem is not specific to RNNs. It occurs in all deep networks, also in deep multi-layer perceptrons. And you can see this if you think of an RNN just as a very deep multi-layer perceptron. And you say that, like, if we have these hidden states and they have a long distance between them, a long path distance between them, then what coming in one hidden state does not affect the other hidden state anymore, and then this generalizes immediately to multi-layer perceptrons. Again, to see this, we draw a recurrent neural network as a deep multi-layer perceptron. How we're going to do that? Well, we have first a standard definition. We unroll that in time. We write it a little bit differently, and then we rewrite it a little bit differently again. So actually, that's the same model. It's just graphed differently. So it looks like a multi-layer perceptron, right? And then we add the missing connections from the model, but now it looks actually like a multi-layer perceptron, right? Like this, the input, we have 4 hidden layers. We have like four outputs. So that's like an MLP. So like RNNs, if drawn like this, you can see that they are deep multi-layer perceptrons. They have weight sharing. Where's the weight sharing? Well, here all these matrices are shared, right? So in a standard multi-layer perceptron, we have no weight sharing, but here we have weight sharing. With sparse connectivity, what does it mean? Not everything is connected to everything. Like this input is only connected here. It's not, and this input is not connected here, right? So it's sparse connectivity. We have skip connections. What does it mean? Like we skip something here. So the input 1 going to the first hidden layer, second input's going to the second hidden layer, third input's going to the third hidden layer. But basically it's still a multi-layer perceptron. It's just deep. How deep is it? It's exactly as deep as the length of the input, right? So RNNs are deep nets, and if the distance between 2 hidden layers is big, then this hidden layer does not influence the next hidden layer. And what has been known there is lost along the path, right? This information is going to get lost along the path. And then you can also right away imagine that this will also happen in a deep multi-layer perceptron, that things are getting forgotten under certain conditions, like the activation function or the size of the weight matrix, right? Okay, so which remedies can we do? So first we look into very simple remedies, like what can we do to address vanishing gradients? So first one is we take L1 or L2 regularization on the recurrent weights. So if we do regularization, that means we want our solution to be small, right? So that was the idea of regularization. Keep most W0 to get a solution that is that generalizes, right? So in this way, we can address the exploding gradients quite naturally, right? Because there we wanted to keep W small, so the gradients are not exploding. Another thing is, if the error derivative dE by dWik is too large, set it to just some fixed constant, right? So that's also called gradient clipping. We compute the exact gradient by backpropagation. If it exceeds 1,000, we just set it to 1,000, right? So maybe that's our upper bound. Or if it exceeds 20, we just set it to 20. So here's a picture that illustrates that. So we have our our method that is like optimizing, going into the direction of the minimum, and at one point, well, the error function is very strange here. If we make a little bit of an error, it says, well, you should go very far away from that point here because you're going in the wrong direction. Because here it's increasing, right? So it says like want to minimize, so we want to go down, and then if we go in the wrong direction, it tells us you should not go into this direction because here you're increasing the error, right? So it tells you go very far away from here. So, and if you're doing that, well, you go very far away, but if you do the clipping, maybe you only go a little bit, right? You don't go as far away as you would have otherwise. Good. Another thing is, so we had two conditions, right? We said we had two factors. The first factor was the weight matrix, right? And it should not be too large, neither be too small. So the optimum is the identity matrix. So because the norm of the identity matrix is 1, so having a norm of 1 is cool. That's good. And the activation function, right? And there we said linear would be best, but we said like intuitively from the repertoire that we know, second best would maybe be the ReLU function, because that at least for the positive region, that also has a derivative of 1, and it's not linear, so it's not going to be a linear network. So we have W initialized as identity matrix and ReLU activation function, and intuitively that should work out fine, right? So there's a paper where they call this RNN, so it's just a RNN with this initialization of W and ReLU function. And what they show in their paper is if they use these IRNNs, they compare that on some task, and they compared IRNN, so this is the accuracy on the test data over the epochs of the network. If they compare that to LSTM, which we see later, they're performing much better, and they're also performing much better than RNN with a 10H function or just the standard RNN with a ReLU function, right? So they say, okay, here we have our problem, and on this problem, the IRNN, which is just very simple, simple initialization and modeling of RNNs, works quite well. Good. So next thing that we're going to talk about is gated recurrent units and LSTMs, and these are more advanced techniques to counter vanishing and exploding gradients. Alright, let's discuss how vanishing gradients can be addressed by either gated recurrent units, GRUs, or long short-term memory units, LSTMs. So here's the basic illustration of an LSTM, and we'll see more about that in the upcoming slides. But the basic idea is you have some input at time step 1, for example, and you have gates in your network, and these gates determine whether or not this input may flow across subsequent time steps. Like in this case, you see here the gates are open, so this gate is closed, so that cannot be transported to the output. But the gates are open here, so the information can freely flow, and you see this gate is closed here, so no updating can happen from these other time steps, so we can purely preserve some some hidden state information across multiple time steps, and therefore we have no vanishing gradients. So this is the basic idea of LSTMs and GRUs. So what are GRUs? GRUs are more complex hidden units compared to standard hidden units in standard recurrent neural networks. They were introduced in 2014, while LSTMs were already introduced in the 1990s, namely in 1997. However, GRUs, we explain them first, and we put our emphasis on GRUs because they're easier. They're not necessarily better, like most people today use LSTMs, but LSTMs are not necessarily better than GRUs, and GRUs are simple to explain, so we stick with GRUs. So the main idea is already as said, you have gates, and these gates control the memory contents, and with these gates we can transport memory contents over long distances, right? So here, that is not a GRU, that's a standard RNN. What happens here is you have your inputs, you have your previous hidden states, you do a linear combination, you have two matrices here, you add them, you put a nonlinearity on top of that, and using these operations, you compute the content of H2, H3, etc. You compute the content of the hidden states by doing linear operations and a nonlinearity. In contrast, we can replace this standard setup with a GRU cell, which is then here in the middle, and it also takes the same input xt and ht minus 1, but then it's doing different computations. And which computations it's doing, we'll see in those slides that are just following. So we need the following notation. We need the sigmoid activation function, and this is really this logistic nonlinearity that takes values between 0 and 1. And why is it this one? Because we have our gates, and we can conceive of these gates of being open and closed. Open is 0, closed is 1, or vice versa, depending on how you want to see that. And we want to have an activation function that maps also from 0 to 1, and we want to have something that can even do this in continuous space. So we don't only want to model open and closed, but maybe also half open, half closed, 1/4 open, 3/4 closed, etc., etc. The other notation that we need here is the pointwise or elementwise product, also called Hadamard product between two vectors. It's just you take the products, you get the vector that has as components the products of the components of the individual vectors. So how does a GRU memory unit look like? So it takes as input xt and ht minus 1, just as a standard hidden unit in a standard RNN. But it feeds them through two gates, and the first gate is called update gate, the second one is reset gate. They look totally identical, except they have different parameter matrices. And keep in mind, these parameter matrices, these are gonna be learned by the model, right? So the model is gonna learn these. We're not gonna set them, but the model is gonna learn these. Once we have computed set T and RT, we define a new HT tilde that's also looking very similar, like a standard RNN, but it has this additional Hadamard product between HT minus 1 W and RT, where RT is given by the reset gate, right? And then then there's another final memory gate the final memory. It's not a memory gate; it's a final memory, HT. So this is the hidden layer value at time step t, and that is computed by the previous hidden layer value at t minus 1. And to this we add ht tilde, which is our new memory content, multiplied by set t, which is our update gate. So these two gates here, they come into play in two different equations. So this is the former setup. Now we're going to look into this intuitively. What is that doing? So we look at two extreme cases. So we make two simplifications here. The first simplification is we don't want to deal with vectors, so we either assume we're in one-dimensional space where we only have numbers. So these are set t. We perceive of set t and rt as numbers, And if you don't want to do that, if you don't want to perceive of them as numbers, you look at some individual component, and one individual component is certainly a number. So that's the first simplification. Second one is we only look at the extreme values 0 and 1, right? So actually it is, these gates can output everything between 0 and 1, and they are soft gates, so to speak, but we look at the hard extreme cases, at the extreme cases 0 and 1 exactly. So let's look what's happening. So if set t, this is our update gate. If set t takes the value 0, then what happens? That's the equation that we have to look at. So set t becomes 0. So this was the bottommost equation, right? Set t becomes 0. So then we have here 1 minus set t, by the way, that's also a vector of 1s, right? But we think we're in one-dimensional case, so 1 minus a number is also a number. So we get ht minus 1. So we have no update. So we can keep the memory from the previous time step, and we can transport. That's how we address the vanishing gradient problem, right? We can transport memory from the previous hidden state to the current hidden state. Now, that's the first cool thing. Then if set t is 1, so if we could set that to 1, we're actually, so what in reality is happening, there's no human who sets these gates to something, but the memory, the network itself is updated and learned, and all the parameter matrices are updated, even those of the GRU unit that has some vectors and matrices, and we have to update them, right? So the network is doing that itself. So if the network decides to set t to 1, we get ht is equal to ht tilde, right? Just following this equation. Okay, so we don't know yet what that means. So we have to look. So we look at the other. So we look at RT, right? Our reset gate. So if RT is 0, then what happens? Here's the equation for ht tilde. So if RT is 0, then this term down here cancels, right? So that cancels. We just get xt times u tan h ht tilde. So that means ht becomes xt u times u and tan h applied on top of that. So it means we're forgetting the past, right? So everything that has previously been said is being forgotten. We only care about the current input. Now we have the tan h function here. Well, that's the traditional way of implementing that. Of course, you could do something else than tan h. You could put relo here if you want that. And the other extreme case is RT is 1. So if RT is 1, we're in the standard RNN, except that we have here a tan h function, which we could replace by anything else, right? So so that is it. Actually, we have already discussed all of the extreme cases, and we have seen that these extreme cases can reproduce interesting patterns. So depending on one of the extreme cases, we can store the memory indefinitely, so we get like no vanishing gradients. We can also say we want to forget the past memory and reset everything, start from 0, so to speak. And note that this was the case when the reset gate is 0, so it's a little bit of a misnomer. It's more, this gate should more be called an anti-reset gate. So when could this happen in NLP? Maybe you have a sentence, you want to determine its polarity, is it negative, positive, or neutral. Imagine you see the word awesome in there, and then maybe that is a good indicator that you should forget everything about the past and just classify this sentence as positive. So this is an intuitive example, which is certainly not always correct, but it could be approximately true. And we can also go back to the standard RNN mode, where the memory is continuously updated based on the past memory and the current input, right? So, and these are just the extreme cases. The network itself can learn to take something in between those extreme cases, right? And that's what makes these GU units really powerful. And here's an illustration of the graphical illustration. So it actually, a standard RNN cell could be illustrated similarly, where we have xt, ht minus 1 coming in. Then we're doing some multiplication and addition with matrices, and we get out an ht. In a GRU unit, in contrast, it looks a little bit more differently. We have these sigmoid activation functions that determine our gates. We take 1 minus is here. We take the tanh function. That could be any. It could also be relu. We add up all of these things, and we get our new memory unit at time step t, right? So this is the graphical illustration. And then there are LSTMs. So they are even more complex, right? And here's the do-it-yourself sign. So you would have to do that. Uh, um, you have to go through that yourself. So it's actually the math is completely identical. There's no additional level of difficulty. It is just a little bit more of the same stuff, right? So it has more gates. It has an input gate for get gate, output gate. These are all informed in the same way. They take as input xt and ht minus 1. And they have different parameter matrices, right, associated with them. And they can be 0, 1, or they can be in between that, right? Then we compute a new memory cell as ct tilde, a final memory cell ct, which is given by adding and multiplying the previous stuff, and then a final hidden state ht, which again is given by ot, is given by. So what is actually OT? So OT is one of the gates, is the output gate, right, which can be 0, 1, and then multiplied by the memory cell content. So it's more complex, but it's basically doing the same stuff. And also here from this graphical illustration, you can see that the LSTM is more complex than the GRU. Good. So we come back to our initial picture, which or like to a variant of the initial picture. In this variant, we're in the traditional RNN, and we see how information is being lost in a standard RNN. So the information comes in, is being output, and is propagated. But because it is added with new incoming information, and because of the activation function, and because of the weight matrices with which it's multiplied, it is being subsequently lost over time, right? So this information just vanishes. In contrast, if we have LSTM or GRU with these gates, we can really control whether the information should flow or not flow, and we can decide that the information should flow over multiple time steps and then maybe be completely forgotten. So that's a cool thing of LSTMs and GRUs, that they can control the flow of information that's going through the networks, and thereby they can address one of the most severe problems of standard RNNs, namely vanishing gradient problems. Good, that's it already. So we had the impression maybe that's going to be complicated, but actually it's not. It was not so complicated at all. These cells are not so difficult at all to understand. I have to say a word on GRU versus LSTM. The LSTM is much more popular, so almost everybody knows that word, and at least until 2018 or 2019, before the transformer became popular, everyone was using the word LSTM. But in practice, in reality, people see that there's not much difference between the two. They perform actually almost equally good, with the advantage for the GRU in being more memory efficient because it has fewer matrices. But people prefer the LSTM, and that could be related to many things, and one of the things could be bias. So we know that the research community certainly is very biased. That has been amply illustrated and demonstrated by the history of deep learning and neural networks, right? And to summarize, recurrent neural networks are very powerful. They have been very popular models of choice in natural language processing until about 2018 or 2019. They're still popular, but they are vanishing because other network architectures, especially the transformer model, are replacing them. And GRUs and LSTMs are special cases of RNNs, and they are more powerful than standard RNNs, or the big class of arbitrary RNNs, and they are more powerful because they can better control the flow of information and thereby address the vanishing gradient problem. In the next lectures, we're going to see convolutional neural networks, which are not so much for sequence classification and temporal classification, like RNNs address sequence classification, sequence tagging, sorry. So they address sequence tagging, also known as sequence labeling, where at each time step you label something, and this is very important for NLP problems because we have many such problems where we have sequential data. This is just a sequence of speech, sequence of text. We want to label each element of the sequence. And in contrast to that, convolutional neural networks are addressing more the classification problem, where we have a sequence, we want to classify the whole sequence, whether it's positive, negative, or something else, right? And then after lecture 10, we have encoder-decoder models, which consist of the concatenation or like the composition of two RNNs or two LSTMs or two transformer models, whatever you want. And with those things, you can do really cool stuff, such as machine translation, for example. And this concludes our today's lecture.